Welcome to a massive open online course on fluidization engineering. Today's lecture part will be on flow regime and its map, basically on liquid solid and gas liquid solid fluidization system. Now, already we have discussed about what is the definition of flow regime or pattern. Still we are looking back a little bit for that. So, this flow regime or pattern means this is the flow behavior and shape of the interfaces between phases in a multi-phase mixture, which is commonly referred to as the flow regime or flow pattern. The flow regime of multi-phase flow in a fluidized bed that we have discussed that depends on several factors like dynamic variables, geometric variables, thermodynamic variables and physical properties of the phases. Dynamic variables like a flow rate of the gas, liquid, or even if solid is in continuous mode, then what will be the solid velocity, and then geometric variables means the column diameter or bed diameter, bed cross sectional area, volume of the bed, even what will be the particle diameter and the geometry of the particle, like what should be the shape of the particles, what is the sphericity. All those variables are coming under geometric variables. And thermodynamic variables are like pressure, temperature, how this pressure and temperature will affect the fluidization behavior in a fluidized bed. And mostly the physical properties of the phases, that is density of the fluid, viscosity of the fluid, and if gas, liquid, solid system, what should be the surface tension of the liquid that will affect the fluidization behavior inside the bed. If you change the density, of course, the behavior will change. Viscosity, highly viscous fluid, it is very difficult to flow or getting different flow regime inside the bed. Even if you are changing the particle diameter, that is coarser diameter, you will not get the specific flow regimes for particular operation. Then you have to change, or that accordingly the flow regime will change and application will be different. And also pressure effect, there will be a at high pressure, if it is operated at high pressure, the minimum fluidization velocity will be more in that case. Now, if we have different flow regimes, of course, we have discussed in earlier classes or earlier lectures that what are the different flow regimes in gas solid system, and what should be the flow regime transition. It is actually nothing but the boundary of the two regimes. Okay, but then what should be the then flow regime map for liquid solid or gas liquid solid fluidization system. Now, liquid solid flow, in that case flow regime for this operation you will get generally two types of flow regimes. One is colloidal dispersive flow regime and another is homogeneous flow regime. This colloidal dispersive flow regimes, in this case conveying of fine spherical particles as a suspension without any turbulence by Brownian molecular movement with Reynolds number of the solid particle should be less than 10 to the power minus 6. So, in that case the colloidal dispersive flow regimes will be occurred, and this type of flow regimes you will get only for the flow velocity, that you can say the velocity of the fluid inside the bed is very low, that is even lower than the Stokes flow regimes. Homogeneous flow regime, you will get that flowing of fine non-spherical particles of low density that holds suspension by hydraulic forces. And in this this homogeneous suspended flow regime actually is resulted at a little turbulence in a range of Reynolds number 10 to the power minus 6 to 0.1. So, in this case everywhere inside the bed the concentration of the solids will be almost similar or you can say the same throughout the column. And in this case the liquid velocity of course will be a little bit higher than the settling velocity of the solid particle. Here see in this diagram, two diagrams are given or this picture is given of first one is for colloidal dispersive flow regime. In this case the particles are moving with a Brownian motion, whereas there is no turbulence in this case, but sometimes you will see some particles are making a colloid with like unstable colloid they are making and coagulating to each other, and then it will be moving as a Brownian motion. Whereas stable colloidal dispersion, in that case there will be no actually coagulation, no actually agglomeration will be forming between the particles. And homogeneous flow regimes, there you will see there may be a chance to form a coagulations since the homogeneous nature, though but it depends on what should be the velocity inside the bed. For higher velocity the breaking of this coagulation or you can say that agglomeration will be a little bit lower tendency relative to the other velocity. So, these are the things that homogeneous flow regimes, how it will be there inside the in the picture it is shown here. Now, of course, it has been discussed what should be the minimum velocity for gas solid fluidization system in particulate bed that we have already obtained from the balance of frictional pressure drop to the weight of the bed. So, in the same way here also we can get the minimum velocity for liquid solid or homogeneous flow regimes for this liquid solid system. In this case also you have to find out what should be the frictional pressure drop from the Argan equation. Argan equation here is this is the part for Argan equation by which you can calculate the frictional pressure drop, whereas this rho p into 1 minus epsilon f plus rho l epsilon mf into z, this part is called weight of the bed or apparent weight of the bed. So, this to be balanced, so that at the minimum velocity for liquid solid homogeneous flow you can get the minimum velocity as a UMF here, whereas this epsilon mf is nothing but the minimum fluidization velocity. This minimum fluidization velocity again you can get from this when and u relationship, that phi s into epsilon mf cube, that almost will be equals to 1 by 14. So, from this equation you can get what should be the minimum porosity or minimum voidage inside the bed for this liquid and solid system. And this epsilon mf minimum fluidization voidage depends on the shape of the particles. For spherical particles it will be the range in 0.4 to 0.45. So, those things already we have discussed earlier. So, this is the way to find out or estimate the minimum fluidization velocity for liquid solid homogeneous flow regime. Now, flow regimes of solid liquid flow, you can say another flow regime is very important, it is called pseudo homogeneous flow regime. In this case flow of particles need some more turbulence, so that the particles will be suspending with very low velocity, but with a little turbulence, and the Reynolds number range for this will be 0.1 to 2, and of course, for getting this turbulence you have to apply more velocity compared to the minimum, and also what is the homogeneous flow regime system. And of course, for this more velocity the particles in these pseudo homogeneous flow regimes are getting suspended, and to keep suspended you have to maintain that velocity, of course, greater than the homogeneous flow regime velocity. A certain degree of segregation in this case also can be permitted to get this pseudo homogeneous flow regime. And to maintain equal conditions for solids of any density at the this Reynolds number range of 0.1 to 2, the ratio of the settling velocity of the particle and the fluid velocity must remain constant in this case. So, if you are maintaining the ratio of settling velocity and this liquid velocity in this bed, you can expect this there will be a uniform suspension of the particle inside the bed with this range of Reynolds number. So, here this is the pseudo solid liquid flow seen in this picture, that here there will be no actually uniform concentration inside the bed, because there will be some voidage that will be distributed inside the column, that is not uniform throughout the column also, and also particles may be agglomerated inside the bed, but this agglomeration also may be in such way that little bit nearer to the value of this uniformity of the solid particles compared to the homogeneous flow regimes. And other that is called heterogeneous flow regime. In this case, of course, you will see the disorder mixture flow of the particles inside the bed. In this case, the velocity should be little bit higher than this pseudo homogeneous flow. In this case, the Reynolds number should be greater than 2, and segregation of the particle, of course, will be seen by this flow regime. And in this heterogeneous flow regimes, lower velocities can sometimes result to conveyance by saltation, and finally to the so called critical deposition velocity inside the bed. In this case, the solid particles begin to settle out, and at this point the pressure drop of the mixture will be minimum. So, heterogeneous flow regimes you can get it from Reynolds number is greater than 2 with little bit higher turbulence here. So, see this picture here, this is the turbulent, you cannot observe here what should be the exactly uniformity or uniformity pattern inside the bed. There will be a internal fluid circulation inside the bed with these solid particles, and since the Reynolds number is greater than 2, there will be a more turbulence inside the bed, and the shape of the particles may not be the same inside the bed, or you can operate these heterogeneous flow regimes with coarser particles with more than higher liquid velocity also. And now see rheological behavior and the solid liquid flow regimes inside the bed. Here see in the table it is seen that homogeneous flow regime you can get for the Newtonian fluid if its concentration, that means concentration of the solid particle inside the bed is less than 25% by volume, and you can get the transition from homogeneous to pseudo homogeneous flow if the Reynolds number of the particle is greater than 0.1. Whereas pseudo homogeneous also for this Newtonian flow that means viscosity will be linear with respect to liquid and gas. In this case there is no gas, so only liquid. So, Newtonian fluid if is less than 25% by volume, you can get the pseudo homogeneous flow, but here the Reynolds number will be is greater than 0.1 and less than 2. Whereas, heterogeneous flow behavior, in this case Newtonian flow behavior also you can get if the concentration is less than 25% volume, but Reynolds number should be greater than 2. This Reynolds number is defined based on the terminal velocity of the solid, like here rho p into u p. This is here R e s, you can say R e s will be equal to rho p or rho s into u settling velocity into dp particle diameter divided by viscosity of the liquid. So, this is your RES. So, based on this RES you can just divide what should be the flow behavior with the concentration less than 25%. Now, at certain certain concentration which is greater than 30%, the slurry starts begin as a non-Newtonian fluid. What is that Newtonian and non-Newtonian fluid? Newtonian and non-Newtonian fluid, actually you know that whenever stress, liquid stress is directly proportional to the shear rate, then you can get it is a Newtonian fluid. Whereas, this shear stress, if it is not directly related to the shear rate, then it may be non-Newtonian fluid. We have also learned in different fluid mechanics books also, you can get also, you just go through more fluid mechanics books, they are the how Newtonian and non-Newtonian fluids are classified and differentiated. So, based on this shear stress and shear rate relationship you can classify. You can say, okay, if suppose shear stress is denoted by tau, then tau should be directly related to the shear rate, like du by dy. Here du is nothing but the change of velocity with respect to the length. Suppose if there is a flow is flowing like this in a pipe, then what should be the y, that is here in r, you can say here in this y direction, or you can see in the r direction here, then the velocity, what should be the change of velocity in this direction, then the gradient of this velocity this radial, or you can say the axial direction, this will be represented by du by dy, and this is called shear rate, and this shear stress is directly related to the shear rate, and this proportionality constant is called mu. This mu is called the viscosity of the fluid. Now, this if it is directly related, that means it is Newtonian. This type of relationship is actually obtained for the like water, so it is called Newtonian fluid. If it is not directly related to this shear rate, then that means here tau, if it is related like this k into du by dy to the power n, that is non-linear relationship, then this k and n will give you the what is the tendency of what should be the behavior of the fluid. Now, if k and n are changing, it is not, if k is not mu, that means here then n is not 1, then you can say it will be totally non-Newtonian. That means n maybe is less than 1 or greater than 1. So, it depends on the type of fluid. So, those fluids will be called as non-Newtonian fluid. So, whenever liquid and solids will be flowing in a 5 or in a column, of course, it will behave like a non-Newtonian fluid also, if the concentration of the solid inside the bed is greater than 25%. So, in this case the viscosity of course will change. Viscosity, it will be highly viscous, and that viscosity will be related to the viscosity of the that is Newtonian fluid. So, that effective viscosity may be as per Einstein's theory, that you can say that viscosity of the non-Newtonian fluid or slurry system, that will be is equal to mu L, that means not without slurry, you can say only pure liquid, then into 1 plus here 2.5 into 5. 5 means volume percentage of the solid inside the bed, and 2.5 here this okay, this will be your effective slurry viscosity inside the bed. So, in this way you can calculate what should be the flow behavior inside the bed. Now, if you run the fluidization with the higher concentrated solid particles, then you can calculate, you have to calculate the slurry viscosity not as a Newtonian, it will be non-Newtonian fluid flow, and the viscosity will be something different. Now, solid particles can be conveyed upward if the transport condition is well satisfied. That means, when fluid velocity exceeds the terminal or settling velocity of the solids. Here see, if settling velocity as hindered settling, it is called hindered settling velocity. In this case, this hindered settling will be is equal to settling velocity into 1 minus epsilon s to the power n. Here this epsilon s is nothing but the solid concentration by volume. So, this hindered settling you can calculate, that means here if particle concentration, that means this slurry concentration, you can say that the bed is higher than this individual settling velocity of the particles may be reduced by the interaction of the other particles. In that case, effective hindered settling velocity would be equal to this settling u set of particular, that means single particle settling velocity into 1 minus epsilon to the power n. This epsilon s you can obtain what should be the ratio of solid volume to the total volume inside the bed. So, V s is nothing but the solid volume inside the bed, and this V s plus V L are nothing but the total volume inside the bed of solid and liquid respectively. So, from this ratio, that is called, this is nothing but a fraction, this fraction, this is by volume, you can calculate what should be the solid concentration by volume inside the bed. And here settling velocity for individual particle, or you can say that single particle settling velocity, that can be of course obtained from the that is balancing by the buoyant force and weight of the solid and its drag whenever it is flowing under this settling velocity. So, from this condition you can calculate this settling velocity for the single particle by this here. So, u set will be equal to 4 by 3 dp 50 by cd into rho p minus rho l by rho l into z to the power 1 by 2. Now, in this case you see CD is called drag coefficient, already we have discussed in earlier lectures that how to calculate the drag coefficient, and here this dp 50 is nothing but the particle diameter at 50%. What does it mean? Thus grain size or particle size at 50% passing sheave. What are the size of the particles, or those particles which are coming down through the sheave will be considered as d50 here, and that d50 will be considered for this settling velocity of this particle. And here this n is coefficient, this coefficient depends on the Reynolds number of the particle, that is given by Weber 1974, and this will be equal to 4.15 into Rep to the power minus 0.063. So, if you know the Reynolds number by this equation here, Reynolds number is equal to rho L u set dp 50 by mu L. Once you know this Reynolds number, what should be the coefficient for n, that can be calculated from this equation. And once you know this n and you settling and this epsilon s, easily you can calculate what should be the hindered settling inside the bed. Now, to get these solid particles conveyed in upward, you have to maintain this liquid velocity inside the bed will be much greater than this hindered settling velocity. So, that is why u L should be greater than u s there. And to calculate this u settling velocity, of course, another important equation for drag coefficient will be calculated based on this Reynolds number. Here this relationship is given. So, from this equation, what should be the criteria for getting the solid particles in the liquid medium to be conveyed upward? So, in this way you can calculate this hindered settling and then criteria for liquid velocity. Now, Liang 1997 they have observed different types of flow regimes of solid liquid systems. So, according to Liang et al, they have actually observed that there should be some conventional fluidization regime in the liquid solid system, whereas other than the conventional fluidization regime like circulating fluidization regime, even transport or hydraulic conveying regimes also are observed. In this case, as they told that if liquid velocity beyond the minimum fluidization velocity, that means u m f that you can calculate, that has been shown earlier, the regime becomes conventional fluidization regimes. It is also for the solid liquid system, not only gas solid system. So, gas solid system also u m f, but liquid solid system u m f we are considering, but it will be calculated in different way, just considering the liquid properties instead of gas properties. Now, circulating fluidization regime, in this case particles will recirculate to maintain certain particular hold up at a certain liquid velocity beyond the conventional fluidization regime. So, in this case circulating fluidization, the main important point is that you have that recirculation will be there at a certain particle hold up inside the bed. That particle hold up is nothing but this volumetric concentration of the particle inside the bed, that can be calculated again by this what should be the volume of solid particles out of the total volume of solid and liquid inside the bed. So, this will be your particle hold up here inside the bed. Now, this from this of course, you have to maintain constant this particle concentration or particle hold up at a certain liquid velocity inside the bed, then only the circulating fluidization regime can be obtained. And transport or hydraulic conveying regime, in this case this flow regime will start if the liquid velocity is further increased to transition velocity to get this transporting or conveying mechanism in the fluidized bed. The radial flow in this case will be non-uniformity and which will becomes the insignificant in the transport or hydraulic conveying regime. So, this is very important that you have to increase the velocity in such way in a certain manner, so that it will be beyond the transition velocity from the circulating fluidization regime. So, for that maybe the non-uniform that is instability manner, instability behavior of the fluidized bed will be observed inside the bed. Now, Liang et al also they have given one flow regime map for this liquid solid fluidization system, where they have represented this flow regime map as per that Kuhn and Levenspiel model based on this U star and dP star definition. So, here dP star they have mentioned in an x axis, again it is defined as the dP into rho L g into rho s minus rho L by mu L square to the power 1 by 3. And in y axis they have defined this U star as U L into rho L square divided by mu L into z into rho s minus rho L to the power 1 by 3. It is very interesting that here liquid velocity instead of gas velocity, and also this density of the liquid it is considered instead of gas velocity for gas solid fluidization velocity. So, in this case since it is liquid solids, the density and viscosity of the liquid will be considered. So, if we see this graph here for flow regime map for liquid solid fluidization, you are just observing here that this profile, this locus, this dotted line, this locus is represented for minimum fluidization velocity in this liquid solid system. That minimum fluidization velocity is being calculated based on that the balance of the frictional pressure drop, which is being calculated by Ergun equation or by experimental data balance with the apparent weight of the liquid solid bed here. So, this equation you can get. So, this UMF is a function of this dP star, and this line, this dotted line is represented for the terminal velocity or setting velocity of the particle inside the bed in a liquid solid system. Now, below this terminal velocity you will get this conventional fluidization regime and with this dP star. So, this is your conventional fluidization system for this liquid solid fluidization, whereas beyond this terminal velocity there will be a certain velocity, and beyond that velocity also you will get different type of flow regimes. Sometimes up to this region will give you the circulating fluidization regime. Even beyond this critical velocity that is represented by U A, beyond this critical velocity you can get the transport regime, by which the solid particles will be transported upward by this high liquid velocity beyond this U A. Now, this important point is that here you can get different flow regime just simple from this map by calculating what should be that. Now, if you want to have certain flow regime condition, now what should be the U star based on the fixed dP value. Suppose here one point is there. Now, question is that you have this dP star is fixed, like what is that dP particle diameter, and what is that liquid density and gravitational acceleration, of course, it is fixed, particle concentration is also fixed, and the density of the particle is there certain, and the density of the liquid is there, viscosity of the liquid you know, then you can calculate what should be the dP star. Now, once you know this dP star as this, like here suppose this point, what should be the dP star here, some value, and corresponding to this value of U star, it is almost 1000, no sorry, it is 10. Then this 10, from this 10 that means this U star will be equal to 10, U star is equal to 10. Then from this what should be the U L, just dividing this this portion of this, then U star divided by this, that is 10 by this value, then you will get what should be the value of UL. Then you have to operate the fluidized bed with this liquid velocity, so that you can get this transport regime. Now, suppose if you want to get the conventional fluidization regime here and with a certain liquid velocity, then what should be the particle diameter to be taken here, so that you can get the conventional fluidization regime. Now, if your liquid velocity is 1 only, 1, that means here U star is 1, then corresponding what should be the U star here, and then UL, if it is known to you, then what should be the particle diameter you can calculate from this value. So, from this flow regime you can get the idea what should be the particle size to be taken to get this particular fluidization regime, or if your particle size is fixed, then what should be the fluid velocity inside the bed to be maintained to get this particular fluidization regime. So, you can calculate it from this fluidization map. Now, of course, you have to know what should be the transition of this different fluidization regime inside the bed. Now, minimum to conventional fluidization regime, of course, you have to maintain the liquid velocity in such a way that you are just going to change the minimum fluidization to its conventional fluidization with this liquid solid system. How? Now, you have to calculate the minimum velocity, that means minimum velocity. If your dp star within the range of 3.50 to 100, then what should be the minimum fluidization velocity? Now, to get the conventional fluidization velocity, you have to take the, or you have to consider the velocity of the liquid just greater than this minimum fluidization velocity. So, from this correlation you can get, you can calculate, or you can get the idea what should be the velocity for liquid for this conventional fluidization. Another transition for conventional fluidization to circulating fluidization regime. Suppose if you want to work with circulating fluidization regime with this liquid solid system, then you have to have what should be the, or you have to have an idea what should be the velocity of the liquid to be maintained inside the bed, so that I can get the circulating fluidization regime. So, for that you have to calculate critical velocity or transition velocity by this correlation, and this correlation will give you what should be the critical velocity for liquid. Now, you just to increase the velocity, or you have to take the velocity of the liquid just beyond this critical velocity, so that you can get circulating fluidization regime. And then how to get the transport fluidization regime or transport or hydraulic conveying regimes for this liquid solid slurry system in the fluidized bed. Here also one correlation is developed, and it is given by Liang et al. 1997. So, that you can get the hydraulic conveying regime just by this criteria. In this case also you have to calculate the velocity from this correlation, like by knowing the viscosity of the liquid, particle diameter, even solid density, and calculating by this equation what should be the value. If this value is if your liquid velocity is greater than this value, then you can say your fluidization will be operating with the hydraulic conveying regime. Now, coming to the point here, the flow regime in the 3-phase fluidized bed system. You will see the flow regime, whatever regimes we got from liquid solid or gas solid system, the flow regime for 3-phase system of course will be something different than this earlier one. Now, in this case 3-phase system, here gas, liquid, solid 3 phase will be interacting to each other, and it will change the flow regime map and also flow regime transition because of that simultaneous interaction of the gas, liquid, solids inside the bed. Now, here see one diagram here shown, this regime map. In this case, there are several flow regimes are shown here: dispersed bubble flow, discrete bubble flow, coalescent bubble flow, slag plug flow regime, churn flow, breezing flow and annular flow. So, all these 1, 2, 3, 4, 5, 6, 7 flow regimes are generally observed in gas, liquid, solid fluidized bed just by changing the liquid velocity and gas velocity inside the bed. Now, if you keep the gas velocity constant and if you increase or decrease the liquid velocity, you will get this dispersed bubbly flow regimes here. That means, for low gas velocity and low liquid velocity, there is a possibility to get this dispersed bubble flow. In this case, bubbles are dispersing in an uniform fashion, and all the bubbles are almost uniform in size throughout the bed, and gas will be dispersed as a dispersed phase of these uniform bubbles with the solid particles also. And then if you increase the liquid velocity for this low gas velocity, you will get another dispersed bubble flow. It is called discrete bubble flow. In this case, the concentration of the bubbles will be lower than the earlier one. So, dispersed bubble flow. In this case, the coalescence of the bubbles may be not possible, but they are separately moving up to the top of the column. So, all the bubbles, individual bubbles will be moved up, there will be no interaction, but there will be very less interaction will be there, but there may be a chance of interaction of solid particles and gas particles and liquid particles, but bubble interaction will be little bit lower. Whereas, in coalescent bubbles, in this case interaction between bubbles and the solid particles will be higher. So, in this case, whenever the interaction of the gas bubbles will be there, there may be a chance of coalescing of the bubble. Coalescing means what? Two bubbles or three bubbles will come together and make its bigger bubbles. So, they will come to each other and they will conjugate and it will become bigger one. So, in this case, the formation of the bubbles will be totally non-uniform. That means, here some bubbles will be more bigger, some bubbles will be more finer, and there will be a continuous coalescence of the bubbles will be there. Those bubbles will be coalescence, they will go up very fast due to their buoyancy effect, and those are not coalescing, they are moving slowly to the up. And whereas, the solid particles sometimes will take part to the interaction that may hinder the coalescence part. Sometimes the in between two bubbles, if there is a solid particles, then coalescence may not be possible. So, they may clog to the solid particles and go off, but whereas, if there is no particles in between two bubbles, they are immediately coalescing and go up. So, this type of phenomena is called coalescent bubble flow. Whereas, if you increase little bit this gas velocity by keeping this liquid velocity at fixed, then you can get this another type of flow regime. It is called slag or plug flow. In this case, you will see big bubbles will move just as a chain was to the top and chain wise to the top, along with some smaller bubbles and with the solid particles. So, in this case, the bubbles will be non-uniform in shape, not will be spherical. It may sometimes form this bullet shaped bubbles. So, this type of is called slag flow. But this bullet shape, sometimes if this bullet is just the bullet cross section, the lower part of the bullet cross section will be occupying total cross section of the or almost equal the cross section of the bed, then you will see it will be the flat slag and also flat slag with the bullet nose. So, this type of bubbles will be moving up as per this. So, here this is called this slag flow, whereas if bubbles are bigger, but it will be not exactly the cross sectional area or the diameter, its diameter is not the same as the diameter of the bed, and but it is larger and it is the shape is like that one slug, then maybe it is called as a plug flow. Whereas, if you increased more gas velocity, then what will happen? You will get the churning phenomena inside the bed, that is called churn flow. In this case, the bubbles will not give you the special form of round shape or whatever, but maybe it will be elongated and this gas will be spreading inside the bed like this shown in figure like this here. So, this is called churn flow. In this case, high turbulence will be there, more interaction will be there. Here the continuous coalescence and breakup will be there inside the bed. So, this is called churn turbulent flow. And breezing flow, in this case you will see bubbles are moving upward, but there are some formation of the breeze type breeze like bubbles, and that is why it is called this breezing flow here. In between two bubbles there will be a density of the solid particles will be more higher inside the bed. Whereas, this annular flow, if you increase the gas velocity again at a certain liquid velocity, you will get the annular flow. In this case, to the center of the bed you will see gas will be flowing continuously without breaking of that surface, that means here continuous gas flow will be there, but surface between solid and liquid or surface between gas and liquid will be in such a way that there will be no uniform surface formation, there will be some zigzag surface formation inside the bed. So, it is called annular, that means the central core region of the bed the gas will be moving up, whereas in adjacent to the wall the liquid solid slurry will be flowing. So, this type of phenomena is called annular flow. So, in 3-phase fluidized system we can get this 7 type of flow regime inside the bed, based on the gas velocity and liquid velocity changing. Now, let us discuss the behavior of this different flow regime. Now, what is that? Now, discrete bubble flow, what is that? This discrete bubble flow pattern actually predominates at low gas and liquid velocities. The flow pattern is characterized by the small bubbles with relatively uniform size distributions. The bubble size and its distribution in the discrete bubble flow pattern are influenced by the gas distributor. At low flow velocity, when a small amount of gas are introduced into the column or bed, you will see small bubbles appear, and the number of bubbles and the gas hold up of course are also very small, and bubbles do not have sufficient time to coalescence, since their separation distance is large in this case, and of course, this distance will be larger compared to the size of the bubble. The bubble frequency increased if you gas velocity increased. Of course, this will be linearly proportional, and the bubble, of course, that is why it is called bubble frequency increased linearly with the gas velocity here. Now, in case of dispersed bubble flow, the dispersed bubble flow pattern is encountered at higher liquid velocities. The bubble flow pattern is characterized by the small bubbles with more uniform in size distribution than discrete bubble flow pattern. As a result, you will see the liquid turbulence will be little bit higher than the earlier one. At high liquid velocity, dispersed bubble flow is exist because the solids hold up of this 3-phase fluidized bed decreases towards 0 as liquid velocity is increased. As reported by Zhang et al. 1997, they observed that in case of air water and the particles with 1.5 millimeter glass beads, the discrete bubble flow pattern may not be exist there. Coalescence bubble flow, in this case this flow pattern is restricted to a very narrow gas velocity range depending on the bed diameter. Now, larger bubbles of wider size distribution are encountered with increasing gas velocity. As their population increases, the distance between individual bubble decreases. Small bubbles sometimes travel with lower buoyancy, and in this case the overall behavior of the multiphase mixer is represented as a coalescent bubble flow just by coalescing of the smaller bubbles to make it larger bubbles. And bubble coalescence is more intensive in air water system containing glass beads less than 2.5 millimeter in diameter. Then the corresponding gas liquid system, since the particles increases both the emulsion phase viscosity and the density. Here important that see why coalescence bubbles flow, will observe that here viscosity, physical properties of the fluid is very important. Okay. In this case, if you increase both the viscosity and density of the slurry inside the bed, you can have the different phenomena of the bubble coalescence. The tendency, or you can say that intensity of the coalescence of the bubble inside the bed will be higher. The pattern, of course, the gas passes through the liquid solid mixture as bubbles of irregular shape and larger in size, and this differs from the 1.5 millimeter glass bead system, where bubbles are spherical or spherical caps in the coalescent bubbles flow pattern. So, this flow patterns depends on the shape of the bubbles also. This coalescence behavior that depends on the shape of the bubbles. In this case, you will see the coalescence phenomena will be more easier for spherical compared to the non-spherical bubbles. Sometimes caps type bubbles will give you the easier coalescence compared to the other type of other shape of bubbles. Of course, this coalescence behavior depends on particle diameter also. For more finer particles, the coalescence behavior will be higher than the coarser particles. Slug flow, as the gas velocity is increased further, then bubbles become larger and more elongated, and some bubbles cross sectional dimensions approach the diameter of the column. So, this phenomena, so that is why slug will form. The appearance of Taylor bubbles, that means bullet shaped bubbles, indicates that the flow pattern has changed to a slug flow. The slug flow pattern spans a wide range of gas velocity here. At low liquid velocity, the onset of slug flow is almost independent of liquid velocity, while at high liquid velocity, the transition from dispersed bubble flow to the slug flow is a function of the liquid velocity. When if you increase the superficial liquid velocity inside the bed, the transition gas velocity from this dispersed phase to the slug flow, that will increase. And churn flow, in churn flow the Taylor bubbles are distorted, and as the gas velocity again is increased, the distorted Taylor bubbles become elongated, and if liquid plugs between successive Taylor bubbles become thinner, then you will get the successive Taylor bubbles coalescence and forms larger bubbles, and you will get the churning condition inside the bed. Whereas bridging flow, in this case you will see a liquid extends over the core regions of the column at high gas velocity, and this flow pattern of course limits the liquid film occupying the annular region of the column in any cross section. In case of annular flow, you will see continuous gas region at the course surrounded by the continuous liquid region at the wall will happen. And in some cases at high gas velocity, small bubbles may entrain in the annular region of solid liquid emulsion. There will be no bubble or solids or liquid breeze at the center of the vertical pipe or column or bed in 3-phase system. Now, here another one example of flow regime map of fluidization for these 3-phase systems are given. Here see this flow regime map is represented by the superficial gas velocity and the liquid velocity. The superficial velocity gas velocity in the x axis and superficial liquid velocity in the y axis. Now, if you change this gas and liquid velocity, you will observe different flow regime in this 3-phase fluidized bed. And this fluidization map, flow regime map is actually made by Zhang et al. 1997 with air, water and steel shot of diameter 1.2 millimeter. Now, this flow regime map it will represent, or it is actually tell you what it will tell you that what should be the dispersed bubble flow for a certain gas velocity, and when you can expect or when you cannot expect, and what should be the transition from one flow regime to the another flow regime. Now, suppose if you want to run any fluidized bed with this air water or air water and this steel shot of diameter 1.2 millimeter in your laboratory. Now, you want to actually run this fluidized bed with a slug flow, then what should be the gas velocity, what should be the liquid velocity, that you can actually obtain from this flow regime map. How? Let us consider this gas velocity. You have one column, fluidized bed column. In this case, one distributor will be there through which gas will be distributed, and this is gas, and again liquid also to be supplied from the bottom here. Now, you want to actually get the phenomena of slug flow inside the bed. Now, coming to this flow regime map here, first consider any location here for this slug flow. Let it be here if gas velocity is equal to 1. If gas velocity is equal to 1, if you are maintaining the gas velocity as 1.0 meter per second. Now, if you are fixing the point here at this gas velocity, then what should be the liquid velocity to be maintained or to be supplied in the bed, at which liquid velocity you can get this slugging condition. Let it be here. If you are maintaining the liquid velocity inside the bed as 10 to the power minus 1, that means 0.1 meter per second, then you can have this slugging behavior inside the bed, slugging behavior. Even fixing this gas velocity, if you decrease the gas velocity, maybe here in this case, then again you can get the slugging behavior. So, by fixing the gas velocity, if you change the gas velocity below this point or above this point of 0.01, you can get different combination of the gas liquid velocity to get this slugging condition, because you are here in this location of slug flow. You can get at this point also the slug flow. Here what should be the gas velocity and what should be the liquid velocity here. So, from this condition you can get what should be the liquid and gas velocity, so that you can get the slugging condition. Now, you want to get the breezing flow. What to do? Now, you have to maintain the gas velocity here at this point here. Suppose here this is 1, 2, 3, 4. This is your suppose 4. So, 4 meter per second, if you are just maintaining the gas velocity as 4 meter per second, then what should be the liquid velocity to get this breathing flow here. Suppose this is the point. So, if you are maintaining this 0.1 liquid velocity and 4 meter per second gas velocity, then you can get the breathing flow. So, this is the nice way to identify which flow regime you can expect for your operation. Now, you can control, you can change the different flow regimes, or suppose if you want to apply the fluidization operation for a particular application where this flow regime is more suitable. Suppose in this case the churn turbulent flow for highly mixing condition to get this suppose reaction and reaction. So, you have to maintain this gas velocity as 2 meter per second by changing the liquid velocity like this here from 0 to up to this here also. So, different way, different combination of the liquid and gas velocity, if you are changing, you can get the different flow regime map. So, this is the map by which you can just obtain what flow regime you can expect from your bed. Now, what are the different transition? Of course, this transition to get the dispersed bubble to coalescence bubble flow, these correlations will be helpful to calculate the transition, or you can say the boundary at which gas or liquid velocity to be maintained. And coalescence to slack flow, of course, the liquid velocity should be less than this correlation, whatever it is. So, for low gas velocity, for high gas velocity, this correlation will be helpful to get this minimum gas velocity to have this slack flow from coalescence flow. Similarly, for other transition of flow regimes like slack to churn turbulent flow and churn to breathing flow, you can calculate the gas velocity, minimum gas velocity for which you can get the transition of the different flow regimes. Now, transition of flow regime, breathing to annular also, this is one diagram from which you can calculate to get this breathing to annular flow, what should be the liquid velocity or gas velocity to be maintained. So, next class onward we will be discussing another topics like pressure drop and other things. So, this is the flow regime map, and flow regime, different flow regimes you can expect for liquid solid and gas liquid solid system. So, that is for all today. Thank you. Next lecture will be continuing with other topics. Thank you.